Hello everyone, and welcome to this video where I'll be taking you through a sample question related to the objective: determine the slope of the tangent line to a parametrically defined curve at a given point. So in this video, I'm going to be at Knewton.com. Here I am in their Knewton Alta program with homework questions. And I'm just going to go over one question related to that objective. And the way I do this one would be similar to the way you do all the other ones in this particular objective. I'm also in this instructor mode, so you can see the correct answer already. So I will, of course, just show you how, they got that value, how they got to that answer. Now, I would highly recommend that if you're somewhat familiar with the material, that you pause the video first, try to work it out yourself, and then come back, watch me go through it, and compare your work to mine, see how well you're picking up the material yourself. Okay, so here in this question, we're asked to determine the slope of the tangent line, also known as the derivative, at t equals 1. It says the value of the parameter t. At t equals 1, to the curve defined parametrically by the equations x of t equals 7 times the square root of 4t, and y of t equals -5 times the square root of 5t plus 4. And of course, these are for values of t greater than or equal to 0, so that you have real number x's and real number y's. And we're also asked to enter your answer as an exact answer. All right, so don't punch it into a calculator and round to so many decimal places, right? Just enter it as a fraction here, as you can see. All right, so they got m equals, you're going to be filling in the blank. What is the slope of the tangent line to this curve defined parametrically at the point where the value of the parameter is 1? All right, so I'm going to go with some paper here, work this out. So the equations for the curve, right, the x-coordinate depended on this parameter called t, and x of t was given as 7 times the square root of 4t, which for derivative purposes, I'm going to write this as 7 times and then 4t to the 1/2 power. Remember, that was the square root to the 1/2 power. And the y-coordinate of any location we're at, y of t, depending on the parameter t in this way, it was given as -5 times the square root of 5t plus 4, which once again, I'm going to rewrite roots as powers, fraction powers, rational powers. So this is equivalent to -5 times, and then the quantity 5t plus 4 to the 1/2 power once again. And they made sure to make a note of this, right? The fact that the value of the parameter is always non-negative, because if the parameter had a negative value, this x-coordinate would be imaginary, right? It wouldn't be real, and we're only going to be looking at a curve on the xy plane where the x and y axis are real number lines. Now, we're focusing on the point where t equals 1. So you know what? I'm going to actually label what that point would be so we can go to Desmos later. I'm actually going to draw in this tangent line. They're only asking for the slope of it, but I'm going to get the entire line. So at t equals 1, we're at the following location. We're there on x of 1, y of 1. Now the x coordinate when t equals 1, I'm just going to say this, 4 times 1 is 4. The positive, non-negative principal square root of 4 is 2. 7 times 2 is 14. Okay, so you're at 14 for the x coordinate. And when the y coordinate when t equals 1, going into the y equation, again, I'm just going to say this. 5 times 1 is 5, plus 4 is 9. The square root of 9 is 3, times negative 5, negative 15. All right, so this is the point that we're located at when the value of the parameter is 1. What I want now, and what they're asking me for in the problem, is what's the slope of the curve, right? The derivative, the slope of the tangent line to this curve at this point. So recall from, again, hoping you're familiar with some of this before you got here, right? Seeing maybe previous videos of mine, or you're doing some reading, studying, that if you want the slope of the tangent line to a curve, right, that's represented by this dy over dx, or you could say y prime of x. But when the curve was, represented parametrically, right, the x and y coordinate depended on, say, t here, you could rewrite this equivalently as dy over dt divided by dx over dt. Almost as if you were dividing the numerator and denominator by dt, even though, again, technically that's not what's happening here, but these turn out to be equivalent. So, to find the slope of the tangent line to our curve anywhere, we can find the derivative of y with respect to t, and then divide it by the derivative of x with respect to t, and we have y in terms of t, x in terms of t up here. So let me find those, right? So we have x given in terms of t. So we find dx, dt was the derivative of x with respect to t. I'm going to go through some rules here. I'm assuming you know how to find derivatives of your pre-calc functions all from Calc 1. So that constant multiple stays 7 times, and then here something to the half power. I would do the power rule, do half times that 4t to the negative half, right? You bring the power down, subtract 1 from the power. But then chain rule, multiply by the derivative of the expression inside, so times 4. And if I totally simplify this, half of 4 is 2 times 7 is 14. It'd be 14 multiplied by, 4t to the negative half power. Which I'll leave it that way. But we're gonna plug in 1 in a second, because that's what we're focusing on. We're at the point when t equals 1. All right, then I'll do something similar for y prime, right? dy over dt, or the derivative of y with respect to t, is negative 5 times, and then again I have some expression to the half. So I'm doing the power rule. It's half of that expression, 5t plus 4, to the negative half power. Then chain rule, multiply by the derivative of 5t plus 4 with respect to t would be times 5. Simplifying a little bit, negative 5 times positive 5, and then times a half, negative 25 halves times, and then this 5t plus 4 to the negative half. All right, so let's go to the point where t equals 1. All right, so the derivative of x with respect to t at t equals 1 is the following. It's 14 times, and then 4 times 1 we're just replacing t with 1, would be 4 to the negative half. Remember, 4 to the half would be 2. That's the square root of 4. And this is a negative power, and negative powers are the reciprocals of the positive power. So this is 1/2. All right, 4 to the half is 2. So 4 to the negative half would be 1/2. So this is 7. All right, so that's going to be in my denominator here. When I calculate dy over dx, right, the denominator at t equals 1 is 7, half of 14. Okay, and then I'm doing the same for dy over dt. Okay, so the y prime, or derivative of y with respect to t at t equals 1, is this expression here. So negative 25 halves times, and then 5 times 1 plus 4, that's 9. 9 to the negative half power is 1/3, right? Because again, 9 to the half power is 3. So 9 to the negative half would be 1/3. This is negative 25/6 when I multiply these fractions. So that's going to go in the numerator here, all right? So the derivative that they're looking for, the slope of this tangent line, which they were calling m for slope. Usually m represents slope, but the slope of this tangent line is negative 25/6 in the numerator divided by 7 in the denominator, and this is at t equals 1. But dividing by 7 is the same thing as multiplying by 1/7. So this 7 would get multiplied by the 6 in the denominator. That's negative 25 over, and then 6 times 7, 42. There we go. That is the slope of the tangent line to the curve represented by these parametric equations at the moment when t equals 1, which is at this point 14, negative 15. All right, so I'm going to we'll go back to the website. You can see that that is indeed the solution, right? Negative 25, 40 seconds, just like I showed you how to get. But I want to also verify this visually. I do like to do that quite often. You don't always have to, right? If you know you're doing something correct, feels good, just stick with it. Obviously, if you have an answer to look at, and you got that, you should probably feel good that you did something right. But I'm going to go to desmos.com here. All right, so this is desmos.com, free online graphing calculator. And I'm going to enter those parametric equations we were given for the curve. So to enter parametric equations in Desmos, you have to enter it as an ordered pair. So left parentheses, the x coordinate was 7 times the square root. You can just go SQRT and the square root symbol shows up. 4t inside that. And then right arrow to get out of there, comma. And then the y coordinate was negative 5 times the square root of 5t plus 4. All right. And let's see. Seeing part of the curve down here. Part of the curve down here. I'll make this, t has to be greater than or equal to 0, right? No negative values of t because I want real number outputs here. Let's go, t equals 0 to from 0 to 10 just to see more of the curve. So seeing this part of the curve show up. Now, all I really care about is that point when t was equal to 1. And I'll label that point. That point was, we said, 14 for the x and negative 15 for the y. And I'll label that. And you can hopefully you can see that that is clearly on this curve, right? This curve that was traced out by the parametric equations. So next I'm going to put in the line that would go through this point with a slope of negative 25, 40 seconds, right? That was the slope of the tangent line, that dy over dx I showed you how to get. So I'm just going to put that in slope-intercept form. No, point-slope form. Let's do point-slope form. Y minus negative 15, so y plus 15. That's y minus the y coordinate of our point equals our slope, right? The slope of this line should be negative 25 40 times the quantity, and then the change in x minus, and then the x coordinate of our point is 14. And maybe I'll make it go to settings, change that to like a dashed line or something. But if you look at that, right, that green dotted line, dashed line that's in there now, it's definitely pointing in the same direction that the curve is. And the closer I zoom into that point, that line and the curve are looking like they're almost exactly the same, right? So this definitely is the tangent line to that curve at that moment. Wonderful. Great. All right, so that's how to calculate your dy over dx when you're given parametric equations in 2 dimensions. X and y depend on one parameter t. And I'm hoping that watching me go through this here helps you out when you're working on similar problems on the same objective. And thank you very much for watching.